the time at Hart Scientific and Fluke, I've worked in the Cal Lab in different positions, and I'm currently the Director of Temperature Metrology for Fluke. Today I'll be talking about sanitary temperature sensors. So first of all, we'll spend some time talking about what they are. See some pictures of some different sanitary sensors, and you'll know the commonality with many of these is that they have a flange on them. We'll talk about what that is here in a minute. As I've already said, these sensors are very, very common in a lot of manufacturing environments, in pharmaceutical, biotech, and food. And the sanitary temperature sensors come in a variety of shapes and sizes. As the name, are designed to maintain cleanliness, so they are typically made out of some kind of material that can be easily kept clean and is inert to the chemicals that they're exposed to. Oftentimes it's stainless steel. The category we will be mainly talking about today is the tri-clamp category. We'll talk a little bit more about what that is, but there are other sanitary sensors that may not have the tri-clamp flange on them. So tri-clamp sensor, this is a sensor that has this flange, and what this flange does is allows the sensor to be easily clamped into a pipe or some kind of manifold system. In this case, temperature sensors can measure the temperature in the manufacturing process. Closer look at what the setup looks like. We're joining us today. We are very familiar with this, but we thought it would be good to review in case there's someone who isn't really familiar with tri-clamp. These are. So basically, this is the sensor, and it shows here how there's a clamp ring that goes around the flange and allows someone to easily clamp into a system for a leak-free connection. The factories that we've visited, hundreds or thousands of these sensors installed throughout the different this is where it's important to measure temperature. So if you're calibrating these sensors, we want to go over three important factors for making a good calibration with these tri-clamp sensors. So you need a good temperature provides good accuracy, good uniformity, and repeatability. So ideally, this would include an instrument that clearly identifies what these certainty are, so that you can work at a high level of quality and have confidence in the measurements. Next is having sufficient immersion depth. Sensors, being temperature sensors, need to have proper immersion to avoid due to temperature gradients, because so much mass to it, and oftentimes the sensors are fairly short because they're fitting into a pipe system. If you're able to immerse the sensor a few inches, you may be getting a lot of stem effect in your measurement that could cause error. Third of all is calibration throughput, and basically that's like any calibration. If you can do more than one at a time, that can help save a lot of time. So these are three factors that we felt to make clamp sensor calibration scenario. So typical temperature sources for calibrating sanitary sensors are dry block calibrators. They are called dry block calibrators because they are basically small or furnaces that have typically a metal block that had machined to different hole sizes for a variety of probe diameters. And they are designed to be basically a portable temperature source, so they can be taken into a factory process, and those are installed in them, and then you can cool the dry block calibrator to the temperature you need to do calibration. In order to get better temperature gradients inside the dry block and to reduce errors, they have smaller area to measure in. So you see how large the assembly is for a tri-clamp sensor. That means that that in the dry can typically just put one in at a time. But dry blocks are workhorses of this industry and are very popular. Category is using a circulating bath that's small and portable. Some of these are for calibration. So if they're not designed for calibration, that have the specifications may not be specifications needed for a calibration process, like solidity and uniformity, for example, may not be specified. If they are, they may be fairly large, known uncertainties. A calibration bath is the dry block calibrator. This is a calibrated temperature where the display is calibrated. I should have mentioned that with the dry block calibrators. That's one of the features of a dry block calibrator as well, is that the display is calibrated. You can use that for temperature reference, temperature stability. The difference between the calibration bath and a dry block calibrator is that the calibration bath uses fluid, which is a lot more for measuring sensors of different geometries. So at Fluke, there are two categories of calibration baths now. There is the traditional micro bath category. It's been around for years, has been a very popular product. They have an accuracy range of about 5 degrees, and very small. The working area is small enough that one tri-clamp sensor is all that you can fit into one. The other category is the new 6109A and 7109A portable calibration baths that are designed specifically for calibrating sanitary sensors, so they have a larger tank, and they're also set up better for use in a clean room. So let's talk about that a little bit more here. So the CNA, I think we'll refer to these as a tri-clamp calibration baths, maybe for the rest of the webinar. They have a tank, and if you can see on the right-hand side here, the lower picture shows 4 sanitary sensors and a reference temperature sensor in the tank. So you can increase throughput, first of all, and have a wide range that covers the needs of these calibration processes. As we went out and visited with this type of instrumentation, this temperature range covers definitely the majority of needs in factories. 109A goes from 35 degrees up to 250 degrees, and then the 7109A goes down to -25 and up to 140. The accuracy is 0.1 degrees C, and this is a calibrated accuracy, or we're trying to move from using the word accuracy because it can be so confusing on what that means, and adopting terminology like maximum permissible error, even though I'm not sure that's exactly any more clear. But anyway, this, as always with a Fluke product like this is comprehensive. This includes calibration uncertainty, or uncertainty of the reference standards used to its traceability for this instrument. It covers stability, uniformity, in the tank and repeatability. So in essence, this is the measurement uncertainty. You want to look at that way, is 0.1 degrees C. And you can see in the pictures, this is our first product we made with stainless steel paint on this. And the stainless steel provides more cleanliness, so it can be cleaned with chemicals required to take one of these into a clean process area, like in a food plant. And of course, still also is very rugged and does harbor bacteria and things like that that people need. They need a type of performance calibrate in these areas. So, and also portable, has a big, nicely balanced handle on top of it. The handle might be kind of hard to see. It's over here in the low right-hand corner picture. And there are also handles on the sides on the bottom between the front and rear feet, so that you can, if you have this on a bench, you can reach underneath on each side, and there are handles up under the frame to make it. You can move it a bench or on a cart if you can't up and lift the handle. They are fairly heavy, so the handles are strong for that. Already talked about the sensors vary a lot in length and diameter, and can be a very big challenge for someone to calibrate. The tri-clamp bath, as we are referring to it, is designed to accommodate 4 2-inch diameter full-inch sensors. The tri-clamp sensors do have a variety of diameters. I think they go up to 3-inch diameter. So the tank will hold 4 2-inch diameter flanged sensors, and so when you immerse them, we recommend that you immerse the sensor and also the flange, because it's just such a large piece of mass that can conduct heat where the sensor is at. There's flexibility here. If for some reason you have a calibration application where you don't need to measure the immersed to the flange, then of course you have to. But the key is that it does accommodate that. So in most cases we feel like that's the best route. When measuring the sensors, if the sensor is long enough that it's going to touch the bottom of the tank, then we recommend keeping the sensor 15 millimeters, just a half-inch above the bottom of the tank. Now the sensors, so they directly touch the tank in the bottom. The two methods for calibrating planetary sensors, assuming that these sensors are connected to a typical automation system or control system that in a lot of factories, most of the time this is connected to 4 to 20 milliamp transmitters. Maybe connected by means like to a PLC or something else possibly, but so the control system is used to just generally describe that provides the readout and the measurement and readout of the sanitary sensor. So in the first method, this is where the temperature sensor is disconnected from the control or measurement system. In this case, you take this out of the clamp, put them in the bath, and the display provides the temperature, the actual temperature of the sensor, and you go to either the control room or the PLC display or whatever the control display is, and you see what the control room is measuring for temperature sensor, and then you can make adjustments and then take data again to verify that everything is good to go. Advantages with this is it's a very simple method where the whole system is calibrated. The display and the sensor both are calibrated as a system or as a loop, and you don't have to disconnect any cabling from the system. Is that it may take two to do the calibration, because you may have to have one person in the control room monitoring the display and feeding back to the person out at the site with the temperature sensor. The other method is where the sensor is completely disconnected from the control system. This you again to the clamp system, but you also connect the cable and the sensors in the bath. Sensors if you're just measuring one sensor, you can connect it to input on the bath to measure the sensor. But wanting to measure 4 sensors, then you need to bring in a readout like a 6A that Fluke manufactures, designed for these types of applications, and you can measure 4 or more sensors with the 1586A. Stabilize, then you record the bath temperature from the display of the bath, and then you measure the sensor temperature as displayed on the 1586A. Also, in this, bring in an external probe if you need better sees than what the bath from the display, and that be connected to either the Super DAC and measured by the Super DAC, or it can be connected to the bath because it has reference PRT input. The transmitter, if in this it's using the control a 4 to 20 milliamp transmitter, then you also use the tri-clamp 420 milliamp circuit to do that calibration. So the advantage of this system is that it's a little more in the sense that you are calibrating separate modules or separate components of a system. If there's a problem with one of those, you can isolate and determine if there's a problem. Whereas in a loop cal, you may not see the problem that's happening with the probe or the transmitter itself. The disadvantage here, though, is it takes a little more time because you're doing two separate calibrations in essence. And there's a possibility too that one disadvantage is that at a transmitter cal, you may not be units of temperature, which can also often be a challenge if you're working under FDA regulations. For example, FDA auditors it seems that they don't appreciate seeing calibration data for a temperature system that's in some other units like amps or volts or ohms or something. Some that I'm not sure if it's mentioned anywhere in the slides, but something that was pointed out to me with the tri-clamp bath, though, is that if you are calibrating a transmitter, you can configure a transmitter to display units. We'll talk about that a little bit more when we get to the transmitter section at the end. But though you can quickly put in a config that converts a 4 to 20 milliamp signal to for a unit you want to measure it in, which in this case we would want temperature. We're going to go through an example of calibrating some sanitary sensors from 140 degrees C using the method that we just talked about. So the sensors are immersed in the fluid. There's an optional holster as shown here in the picture that helps hold the sensors in place and helps them to visit at different to change the sensor depth. Before the typical calibration scenario was to immerse the sensor so that the flange also in the fluid. Then After that, you can program in the you want to measure, and the tri-clamp bath automatic sequence through them, and you can assign time to each set point and set it up in a program so it'll run through. And then you start the program, and the unit will lay the status of what's happening. It'll show if it's heating or cooling. It'll give you a status showing if it's ramping up. It'll show that the heating is full power or close to full power, and then once it settles in, it will. I think it says settling on the display, and then eventually, I think it's on the next slide. Once it arrives at the set point and settles in, the light will turn on the top of the unit. It's called the indicator. It'll change from amber to green color to let you know that it's sufficient ability to take. After that, you just record the data that they need, whether it's data from a control room or from 1586. So I like to this picture because it's just able to see how many different sensors are installed in the system. And anyway, it's incredible to see the to support even one manufacturing process in some cases. So another option is to use 1586 and its automation to open up the options a little bit more. So in case you can connect the tri-clamp bath to the 1586A using a data cable, and also use in reference temperature probes if you need to. And of course, you connect the unit test sensor to the DAC stack to measure it. Which allows to have is that you now the calibration from the 1586, and basically it's very similar to the setup we just went through with the clamp bath. You program in the points, then it can save the configuration in file so that you can recall it if you need to use it over and over again. And then you start test, and it will automatically run soak and take data. And when all data is collected, it will be put into a CSV file, and that can be opened in a spreadsheet. And from there, you fill out the calibration reports and then take a break. So, we're going to just a little bit about temperature transmitters too, because the plant is set up to provide 4 to 20 milliamp calibration. So just really quickly, a temperature transmitter it's a temperature sensor like we've already talked about, a PRT that is connected to a measuring head that is of a 4 to 20 milliamp circuit, and basically converts the resistance that it makes on the PRT sensor to a milliamp signal that range from 4 to 20 milliamps, and is variable because the temperature range that's being measured is basically assigned to the 420 milliamp range. So 20 milliamps being the full scale, 4 milliamps being the zero bottom of the scale. Then your measure system. So to account for the accuracy of the 4 to 20 milliamp measurement capability of the transmitter. So the temperature sensor has its own, possibly own calibration, like we talked about. And then, so if you calibrate the sensor by itself, then you also calibrate the 4 to 20 milliamp circuit because it's acting as the readout for the sensor. Calibrate them system. So we're going to talk now about just calibrating the transmitter for the temp itself. So it's calibrated by connecting it to the milliamp loop circuit. This picture. And let's see, am I getting ahead of myself here? I briefly mentioned that this the -P Tri 7109A-P stands for process electronics. So if you BAFs come in two main configurations, without the process electronics board or with the process electronics. Process electronics has 8 terminals. This is for measuring a under test PRT. It has a reference PRT input for, of course, measuring the reference PRT. If you want to use external reference probe, and it has a thermocouple input to measure a thermocouple case. That's what the UUT uses as a thermocouple. And then, first of all, of course, 20 milliamp circuit able to measure at the shot or display. All right. Let's see. I think we've already covered this about inserting the sensor into the bath. You connect transmitter to the 4 to 20 milliamp circuit, and from there, if the transmitter have its own power source, then you can turn on loop power. There's a feature that the Tri-Clamp has. It will power the transmitter if you need that. Others, if it's already powered separately, then you can turn loop power off in the Tri-Clamp bath. And then you adjust the transmitter values that you need to measure and take the readings off of the display of the Tri-Clamp. Now, I mentioned earlier that one is to you either just measure straight milliamps and check against the tolerance of the transmitter, and you can set up to convert the milliamp value into measurement units. And I don't know if all measurement units are available. I looked into that a little bit more, but for sure temperature is available, and you can use I think there's an MX plus B option to do that. So that's basically all we had for today. Looks like we ended very early. We may need to put some more material here this time we've done this webinar. So if you have any thoughts what we need to add to this, if there's something that we include, let us know, and we'll work on it. With some information, if you're interested in the 109A and 7109A baths listed here, and they're available on the Fluke calibration website. So let's see, anything else, Steve? We're already to question time.
Okay, thanks, Mike. We're ready to take questions. If you have any questions, please text those in the chat window, and we'll answer those now. So we've got questions here, Mike. So the first one is, Canon should be used.
So the baths are calibrated using silicone oil, and that's what we recommend if that works for your cal process. Always refer to it. Oh, okay. Let's see. Is there a way to say that for people? Just probably not. It's 200.10 oils, so, 7109A, and then 200.50 oil for the 6109A. So the 50 refer to the Stokes value. Thicker oil is needed for the higher temperature bath, but use other other types of bath fluids if you need to, like alcohol or water or glycol.
This question is, how fast do the baths get to temperature? Information in if you go to our website, we have the brochure posted out there as well as the user manual. There's complete specifications, but Mike, you may comment on this. This is from the manual on the heating and cooling.
So
here.
Typical heating and cooling times for these baths. Let's see, just looking at the table here. So, for example, on the 6109A, that is a heat only. It doesn't have any cooling capability. Bath from 35 to 100 degrees, it takes 25 minutes. So from 100 degrees to 250 degrees takes 45 minutes. And cool from 50 to 100 is 30 minutes, and then 100 to 35 is 55 minutes. So it's down a little bit as it gets closer to room temperature. Then a cold bath, the room temperature up to 140 is 55 minutes, and the cooling time from temperature down to minus 25 is 75 minutes. And time once it, so the times that I just told you, into that, so it will reach the set point, and then within 15 minutes it will settle in for the hot bath, and within 10 minutes the cold bath will settle in to sufficient stability to specifications that are here or published. Here I'm looking at the document, but I realize you aren't looking at that document, so